Let's look at the rift-to-drift transition and seafloor spreading. As I said, there are over 40,000 kilometers of ridges, and so this is an important process in global tectonics. If we look at the rifting to spreading transition, we start with early rifting process where we're thinning the crust in the lithosphere. That leads to eventually the creation of new oceanic crust at a mid-ocean ridge, and that results from mantle upwelling and decompression melting to generate the basalts that form the new oceanic crust. And we also have the development of passive margins on the edges of this new ocean. And how does rifting lead to seafloor spreading? There are several different ideas, and those could include a nucleation at a single point and then zipping up and opening up a new ocean basin. Or it might involve two separate spreading centers that are growing toward one another until they merge and form a single ocean spreading center. Or we might have a more complex idea where there is a spreading center that's forming, it's opening up, and then other places along that weakened zone of crust open up, and those eventually merge. We can look at Ethiopia as an example and look at the controls on the rift location and the segmentation. And in Ethiopia, we're looking at older crust that contains structures like Proterozoic sutures that were part of the Pan-Africa collision. And those form weaknesses within the crust. We also have areas where there was mafic underplating related to a mantle plume. And those create areas within the crust that rifting can begin to take advantage of as it propagates. This area is in the central and northern main Ethiopian rift. You can see the location here. And this lower diagram are the P-wave velocities at 75 kilometers depth, showing partial melt and hot mantle that underlie the central and northern main Ethiopian rift and this other lineament in here. Now we looked before at the Woodlark Basin and how rifting was proceeding to spreading there. This is an active continental rift zone that is creating ocean spreading in its eastern part. And it's developing within a proto-continental crust. So it's a young process. We saw that there was a western propagation of the rifting and spreading. And we looked at the time steps over this process from rifting localization at 4 million years to spreading center nucleation at 3 million years. The propagation of that spreading center and a stop-start process within the development of this rift. And then we saw 1 million years jumping across offsets to next sites of localized rifting. These accommodation zones focus spreading nucleation to the centers of late-stage rift basins where normal faulting and crustal thinning have been maximized. And the early propagation of nucleated spreading segments and the subsequent transform development across non-transform spreading centers typically removes any correlation between the segmentation of the rifted margins, and the spreading centers. We looked at the seismic data for the same area and saw normal faults developing, dropping down basins, those basins being filled with sediments. And we can see from the earthquake focal mechanisms that we see both normal and strike-slip faulting within this system. We also see places in the Woodlark Basin where low-angle normal faults are bringing up lower ductily deformed continental crust in metamorphic core complexes. And these may be in places where magma is less abundant in this rifting system. And we also looked at the evolution of the continental crust from its original width, looked at how that continental crust was stretched and how oceanic lithosphere grew from the east to the west. We also saw that breakup of the continental crust occurred after about 200 plus or minus 40 kilometers stretching. That any of that older crust has now been subducted, and that the onset of spreading at around 3.6 million years propagates westward at a rate of 140 millimeters a year. If we look more closely at the Red Sea, where do we see this rift to drift transition? And in this diagram, just notice the well-developed rift flank uplift in the south, and that's absent in the north. Stepping back, we can see the broader system of the Arabian Plate and the African Plate, with the Red Sea and the Gulf of Aden separating the two. And let's look at this process of rifting that took place starting 35 to 23 million years ago, and then the involvement of the Afar plume, this mantle plume that began about 35 and 25 million years. The Red Sea Gulf of Aden rift system is an example of the various causes of rifting, which include slab pole and the involvement of a mantle plume at around 30 million years. And there's a long sequence of events leading up to the actual ocean spreading in the Gulf of Aden around 20 million years, and in the Red Sea at about 5 million years. Slab pole is taking place along this collisional system in southern Iran. At around 31 million years, we have the Neotethys Ocean, the Indian Ocean here, this Owen fracture zone, the Gulf of Aden, or the proto-Gulf of Aden, and the start of the Afar plume that gave us this basaltic volcanism as part of the mantle plume. This plume is causing diking, uplift, and intrusion of these basalts into African crust. And this process is going on at the same time that rifting is beginning in this area. We see continental rift initiation in the Gulf of Aden and in the Eritrea area at around 30 to 27 million years. At around 24 million years, we're seeing that rifting propagating into the Red Sea. There's rifting and normal faulting extending the crust. The Afar plume is going through a quiescent stage, and the Ethiopian rift is also beginning. Collision begins in Anatolia and Mesopotamia to the north. And spreading is starting, ocean spreading that is, starting in the Gulf of Aden around 19 to 16 million years. By 10 million years, we're seeing spreading throughout the Gulf of Aden. And the Ethiopian rift is linking up with the spreading that's taking place in Afar. And around 5 million years, we're seeing the initiation of a mid-ocean ridge in the southern Red Sea. And currently, we see the propagation of spreading through the Afar region and a northward propagation of spreading in the Red Sea itself. We can look at some gravity data in the Red Sea that suggests that the crust is different at around 21 degrees north. And this suggests that perhaps spreading is limited to the southern Red Sea, and that the northern Red Sea is underlain by stretched continental crust. In trying to reconstruct the Neoproterozoic structures in Northeast Africa and Arabia, it requires that there's a coastline to coastline closure across the Red Sea. And this implies that the entire Red Sea is underlain by magmatic crust. And so it's possible that the Red Sea is a volcanic passive margin. This extensive system of over 40,000 kilometers of ocean ridges is creating about 20 cubic kilometers of new oceanic crust every year. The spreading is occurring along the summits of these broad, gentle ridges. And these are over areas of extensive melting in the upper mantle. And we have several causes of melting in the upper mantle to create this new oceanic crust. The first mechanism is lowering the melting temperature by adding water to the system. And this is a mechanism that would operate in a subduction zone where subducted sediments and hydrated crust can generate fluids in the overlying mantle wedge. The effect of adding water to mantle peridotite is to change the dry solidus from this position to a lower temperature hydrated mantle peridotite. It lowers the melting temperature of the mantle peridotite, and that intersects the geotherm and creates melting. A second mechanism to cause melting would be to add heat to the system and raise the temperature of the mantle, so moving the geotherm to intersect the dry solidus of mantle peridotite. And this is a mechanism that would be associated with mantle plumes or hotspots. A third cause is to decompress the mantle, so to allow the asthenosphere to approach the surface and to move mantle geotherms to lower pressures. That also intersects the dry solidus for mantle peridotite and creates melting. This is the mechanism that would be associated with mid-ocean ridges. The very thin lithosphere beneath ridges allows mantle upwelling, and that leads to the decompression melting that we just discussed. If we look at the thermal structure beneath a mid-ocean ridge, you'll see that the melting that's taking place under the center of a ridge is taking place along these uplifted mantle isotherms. And it's this decompression melting that is the active mechanism for generating melting in spreading centers. Beneath that, we have that zone of mush that is a mixture of crystals and melt at elevated temperatures. If we look at the East Pacific rise and the shear velocities in that region, we see that they're very low shear velocities that show us where the region of melt production lies beneath the East Pacific rise. And it's these dark orange colors that show that the melting is focused beneath the ridge and that the largest melt production is happening under the Pacific plate. The melt generation is strongly asymmetric underneath the East Pacific rise, with that greater melt production happening under the Pacific plate, and there's a greater concentration of melt that's beneath the rise near the Moho. But this hotter Pacific mantle that is generating the melt is leading to a thinner lithosphere over the Pacific plate relative to the Nazca plate. And this is also giving us faster spreading rates on the Pacific plate side, 100 millimeters a year compared to 45 millimeters a year on the Nazca plate side. You can also see this asymmetry in the spacing of the isochrons across the two plates, resulting from the differences in spreading rates on the Pacific and Nazca plate sides. You also see a difference in the absolute migration of these spreading ridges over the last 80 million years. You'll see that there's a correlation between spreading rate and the migration speed. And you can see the differences in just how far different spreading ridges have migrated based on that spreading rate. Now, mid-ocean ridge basalt magma chambers are thin and narrow, centered beneath the ridge. And if you look along the ridge axis, you'll see small, thin melt bodies above crystal mush zones underneath these ridges. Seismic reflection data along the East Pacific rise shows these axial magma chambers along the ridge. And you see that it gives strong and continuous reflections along most of the profile. Now we'll look at two velocity profiles for these lines, 1625 and 2488. These are P and S wave velocity models, and the diagrams showing the crustal structure and the evolution of the axial magma chamber with time. The results show that there's a presence of crystal mush and pure melt in these two profiles. At both locations, the magma chamber is underlain by 150 to 200 meter thick high velocity floors, so solid floors, and overlain by 50 to 60 meter thick roofs that could be solid. The 150 to 200 meter thick low velocity zone above the roof could result from hydrothermal fracturing. And with efficient hydrothermal circulation, it would take about 50 years to cool and crystallize a 50 meter thick magma lens. If we look at the seismic reflectivity beneath the eastern limb of the East Pacific rise, we're looking at an overlapping spreading ridge. The red and the blue colors on the upper surface are reflections from the seafloor, and the orange and blue-green colors on the lower surface are reflections from melt bodies within the oceanic crust. The magma beneath the overlap basin on the left appears to be migrating upwards to the right, where it ponds in a narrow perched sill beneath the eastern ridge axis. These results suggested that the vertical melt transport from the underlying mantle, together with the subsequent focusing of melt beneath freezing boundary in the mid-crust, supplies melt to the ridge axis in this area at least. Now we talked about fast, slow, and intermediate spreading ridges and used the example of the East Pacific Rise as a fast ridge spreading at a rate of 90 to 100 millimeters a year. And we looked at the Mid-Atlantic Ridge as an example of a slow ridge spreading at 10 to 50 millimeters a year. We also discussed this first order control on spreading rate, which is the percentage of the plate margin that is a convergent margin. And so these fast spreading ridges are surrounded upwards of 20 or 30% by subduction zones, including the East Pacific Rise. And the slow spreading ridges, like the Mid-Atlantic Ridge, have a very small percentage, just a few percent of its plate margin is subduction zone. If we look at those cross sections of the typical fast, intermediate, and slow spreading ridges, we see the extreme relief on the slow Mid-Atlantic Ridge with the axial valley and the rough topography compared to the East Pacific Rise with low relief and an axial rise. And I pointed to the Reykjanes Ridge as an example where even a slow ridge might have an inflated ridge morphology because of the heat and the buoyancy from a nearby mantle plume. If we look more closely at the morphology of a fast spreading ridge like the East Pacific Rise, we see the axial ridge, we see transform faults on either side of that spreading center. This is spreading at a rate of 120 millimeters a year. And we also see a small section that is an overlapping spreading center. The colors are indicating depths of 2,400 meters in the red, pink colors to 3,500 meters in dark blues. If we look at the morphology of a slow spreading ridge, like the Mid-Atlantic Ridge, it's spreading at a rate of 35 millimeters a year. The ridge axis is marked by a valley. That's typical of most spreading ridges. There is a jog in the Rift Valley, a 12-kilometer jog. That is a second order discontinuity on one of these ridges. And it shows a first order discontinuity of this Cox transform fault. Here, the colors are indicating depths of 1,900 meters in the red, pink colors and 4,200 meters in the dark blues. Let's look at these ridge discontinuities. I mentioned first order discontinuity of a transform fault. These are seen in both fast spreading ridges and slow spreading ridges. Second order discontinuities would be those overlapping spreading centers, and these might overlap by a few tens of kilometers. These second order segments can persist for several million years, but they can migrate along the ridge axis, and they tend to move in spurts. So a ridge segment can lengthen at rates of several hundred millimeters a year, but then it might retreat for a time before it surges forward again. The ridge tips at a second order discontinuity appear to be dueling as they surge back and forth along the ridge. And they're generally making slow progress in either direction. If we look north along the East Pacific rise, the spreading axis is offset by about 10 kilometers. Here there are two spreading axes overlapping and curving around a small basin that's located in the offset. Third and fourth order discontinuities can consist of overlapping spreading centers that offset the ridge by less than 3 kilometers, so those are third order discontinuities. Ridge segments that are defined by third order discontinuities are 300 to 100 kilometers long, and they've been shown to correspond with breaks in magma chambers. Fourth order discontinuities are either subtle bends or tiny offsets less than 500 meters in size, and those are often called doubles or slight deviations in axial linearity. And we've discussed that magma supply corresponds to spreading rate, and so fast spreading ridges have a large magma budget, and slow spreading ridges have a small magma budget. And we've seen geophysical indications of magma chambers beneath these fast ridges. And we also see exposures of periddotites and oceanic core complexes underneath these slow spreading ridges. We've seen these gaps in magmatic supply along the fast spreading ridges, but in general, again, have this smooth topography compared to a slow spreading ridge. This magma supply is related to the ridge segmentation, so that we see in a fast spreading system closely spaced, abundant magma bodies. In a fast system, the magma supply is continuous, and there are few areas where it's segmented, versus a slow spreading ridge where there are spacings between magmatic centers and the supply is generally poor. If we look at the P-wave structure across these ridges, we can see that it corresponds to the geology that we expect to see in the oceanic crust. These slow speeds correspond to sediments, whether they're pelagic or volcanic sediments. Faster speeds correspond to the pillow lavas at the ocean floor. Still faster speeds correspond to the sheeted dike complexes and diorites or gabbros in the base of those sheeted dikes. We see mafic cumulates at the bottom. And then, of course, we see a petrologic moho and the actual moho separating the mafic oceanic crust from the peridotite in the mantle. This structure may not be the case in slow spreading ridges. Slower spreading ridges have a lower magma supply. Some segments may actually be agmagmatic. This is a sketch of a slow spreading ridge that's separated by transform faults. The inside corners, or IC, differs from the outside corners in that it's more elevated. It's thinner and it's faulted into a blockier fabric. That asymmetry is thought to be caused by the consistent dip of faults from inside corners to beneath the outside corners, so that the lower crust and upper mantle are commonly exhumed in the inner corner footwalls. And near the segment center on the front face of the diagram, hot upwelling mantle decompresses and partially melts and supplies magma to form the oceanic crust. Again, slow spreading ridges could be amagmatic, and the low angle normal faulting that takes place on the mid-Atlantic ridge can lead to exhumation of lower crustal rocks. These can develop into mullions or megamullions. A mullion is a structure that has a corrugated texture. It's in metamorphic rocks and resembles the frames of tall church windows. It could form from slip along low-angle normal faults during amagmatic extension at mid-ocean ridges. And so in this diagram, you see a progression from a high-angle normal fault that rotates, and there's flexural bending and exhumation of lower crustal rocks along what becomes a low-angle normal fault. That process can be ongoing with new high-angle normal faults. The development of these megamullions happens near the end of a spreading segment during a period of amagmatic extension. The development begins when a detachment fault first forms, following a magmatic episode of seafloor spreading, and it ends when the detachment is abandoned when a new fault breaks through, and that crust is weakened by renewed magmatism. Here's an example of one of these megamullions or oceanic core complexes. The Atlantis Massif is along the mid-Atlantic ridge and near the Atlantis Transform Fault. And you see that it forms a relatively high point within the system. Here's another look at the Atlantic Massif. And what you see is this high relief from the center of the Massif and a transition to steep normal faults on the northern side of the range. Here's a perspective view of this oceanic core complex. The transform fault is forming on an inside corner between about 3 million and 2 million years ago. And the domed megamullion is corrugated by ridges or mullions that parallel the direction of fault slip. And a steep west-facing normal fault formed as the megamullion developed, and it cuts the mullions at right angles.